Um, there's a lot of sound coming from your end. Could you mute? Okay, cool. So today we're going to talk about the third section, which is translational motion, right? So I'm just going to do translational motion today, nothing else, right? Um, so write that down as the heading. Translational, translational, or you can call it linear motion. So most of your mechanics questions will probably come around this, right? There's a fair amount of MCQs as well as a fair, I think like one big question in your second part of the paper that has to do with this, right? So this is where you come across the equations of motion, right? So what we're going to do is we're going to discuss the equations of motion, what are the basic concepts behind them, and then we're going to also derive the equations of motion. So the derivation process will help the equation stick in your head, because you'll understand how uh, each of those each of those four equations are derived, right? So let's start with some basic concepts, right? So the first concept we need to understand is this idea called position vectors, right? So what is a position vector, right? So we're going to start off with a few definitions and then build up those equations, right? So position vector is basically a vector that kind of tells you the position or location relative to some other reference frame, right? So um, what I mean by that is, if you think about location, now, for example, I say Zuleka is, let's say we are standing in front of each other, right? And then I say Zuleka is 2 meters. That makes zero sense, right? But if I said Zuleka is 2 meters in front of Malin, that makes sense, right? So the most important thing you need to understand about something like position, when you are explaining position, it's always relative to something else. You can't have like position like floating out in the middle of the air, right? Everything has to be ultimately relative to something else, right? There has to be a reference frame, right? So position vectors help you describe that. So a simple definition of a position vector is basically um, a vector that describes the position of location B relative to A, right? So when I mean vector, what I mean is there is a magnitude and a direction, right? So B, where B is described relative to A, right? That's the only way we can really describe a location relative to something else, right? And that concept is super important because it helps you avoid a lot of confusion when you're solving problems. Like you always have to kind of figure out what the reference frame is, right? So similarly, now that we know what position is, like that's a basic concept that you already are aware of, let's define what motion is, right? So what is motion? Motion is basically if B's position vector is changing relative to A with time, right? Then we say that B is moving relative to A. Okay, so again, this word relative comes into the frame, right? So a simple example of why this is important is, let's say you're on planet Earth, right? Now, relative to the Earth, let's say you're staying stationary, you're not doing anything. Zubeka is standing on the Earth, right? And you're standing still, right? You would say that you're stationary, right? But the truth is, the Earth is rotating around the sun, which means you're rotating around the sun as well. So, are you really stationary? Yes, you are stationary relative to the earth. Exactly, right? So whenever I ask you if you are stationary or you're moving, the first question that should pop into your head is relative to what, right? So everything is relative. That's the important thing. So how do we define motion? It's basically um, if B's position vector is if B's position vector relative to A is changing with time, we say that B is in motion relative to A. Right? So these might sound like super basic things, but it's kind of important to get this basic stuff in your head, right? Okay, so in any of your A-level questions, all motion will be relative to something. If they don't explicitly say it, then it will be relative to the earth. Yeah. So just keep that in mind. Okay. So continuing with definitions, the next definition we're going to talk about is distance. Right. So distance is basically the length of the path taken by an object from origin to destination. Right? So for example, if you started at a point like this and you went all the way to point B, right? This is your origin and this is your destination. This full length, right? The full length will be your distance, right? So this is a scalar quantity. Right? Okay. So speed, right? The rate of change of distance, right? So speed equals delta d over delta t, where delta d is the distance traveled during time t, during delta t time, right? Okay, so that's fairly straightforward. Next important definition, displacement, right? And now things get interesting. Yeah, before that, speed is also a scalar, right? Because it's basically distance, which is a scalar, divided by time, right? Okay, so displacement is what we're going to talk about next, right? So it's the straight line distance and direction between 2 points, right? So this is a vector. So for example, if you had that squiggly path that we had before, right? Displacement is actually the straight line distance and direction between two given points, right? So that's what displacement is. Okay, so it's a vector quantity, and then we have velocity, which is basically the rate of change of displacement. Right? So V equals delta S. So the symbol for displacement is S. Right? Just put it in brackets here. Velocity is V. So delta S over delta T, where yeah, so where delta S is the change in displacement during delta T time. Cool. Okay, so by the way, this definition of V equals delta S over delta T is actually what we call average velocity, right? Because what you're taking is basically the total change in displacement divided by the total change in time, right? But if we, and this is where a bit of math knowledge comes into play, right? If we take this delta T to 0 through the use of limits, this is what we call instantaneous velocity, right? So to get instantaneous velocity, you have to use differentiation. Okay, so you don't really have to worry about that, because in your physics lessons you don't really need to do that, because the equations that we're going to derive won't be giving you instantaneous velocity, and it's not going to really be a problem, because we're going to use constant accelerations, right? And I'll explain why that's important, right? So what you really mostly be dealing with is this concept of average velocity, right? Okay, so any questions so far? All good? All good? Any questions? Okay, sweet. So the next definition is acceleration. Right? Oh, by the way, maybe it might be worth putting the word linear velocity here, and linear acceleration, and linear displacement, because we're dealing with straight line displacements, right? If you want to be like super anal about it, right? And this is it. Also, if you're talking about units, we might as well mention that as well, right? Unit here is meters, and unit here is going to be meters per second. And then acceleration is basically the rate of change of velocity. Cool. So that's going to be ms minus 2. Right? So acceleration is going to be delta v divided by delta t. Right? Delta v is the change in velocity in delta theta. Right? Yeah, again, this is basically average acceleration, and if you want to get instantaneous acceleration, you want to actually differentiate it by taking this to 0. That will be the instantaneous acceleration. Okay, so the difference between this will be a bit more clearer when we start deriving the equations, and I'll explain a bit more about why this is an average. Okay, so now comes basically the tools that you'll be using to solve most of the problems, and those are the equations of linear motion. Okay, so this is the scenario that we're dealing with. We have an object that has a motion, a linear motion, right? And it starts in this location over here, and it starts with the initial velocity of u. It accelerates, right? So it has an acceleration, which I'm going to use a double arrow to symbolize, and it has an acceleration of a. So if it starts with a certain velocity and has an acceleration, the velocity has to change, right? That's the idea behind the acceleration. So we're going to have a velocity at this location of v. Velocity has changed. So this is at time equals 0, right? It has a displacement of 0, and this is at time equals t, and displacement of s. Cool. So let's start with the derivations of these equations. So we're going to start with the definition of acceleration, right? So we know that acceleration is delta v over delta t, right? So what is delta v? The change in velocity. So that's v minus u. That's how velocity has changed, divided by t, right? So if you take this t over here and rearrange this equation and subject u, you get subject v, you get v equals u plus a t. So that is our first equation. Okay, so it's just a simple rearrangement of this equation. Okay. Second equation, right? To derive this, we start with the definition of average velocity, right? So average velocity is basically the total displacement over time, right? What's another way of getting the average? I'm going to call this equation A, right? So if I want to find the average velocity of u and v, correct, right? So another way of getting average velocity is u plus v divided by 2, right? So that's equation B. So you can then equate A and B, and you have s over t, u plus v over 2, right? And then you can do a bit of rearrangement again, and you can get s equals u plus v divided by 2 into t, and that's our second equation of motion. Cool. Then the rest is basically, you can use these two to kind of figure out the rest. So from 1 and 2, right, what you can do is, for example, which one shall we do first? S equals ut plus half at squared. Okay, so what you can do is you can replace v, right, using equation 1 in equation 2, and let me do the derivation and show you. Becomes u plus at divided by 2 into t. So there will be a 2u here divided by 2, it will be a u, and then there will be this t will get multiplied into that, so it will be ut, and then you get half a t squared, right? And that will be our third equation. Okay. And then finally, if you take 1 and kind of subject t into it, so you take 1 and subject t, you get v minus u over a, right? V minus u over a, which is the same as v equals u plus at, right? And then you substitute in 2 for where t is. Then you get s equals u plus v divided by 2 into v minus u divided by a. Right, so I'll actually write this slightly differently so that you'll actually see the important step here. U plus v can be also written as v plus u. So what is v plus u into v minus u? Yeah, so what is v plus u into v minus u? What do you get? Yes, difference of two squares, right? Into divided by 2a equals s. And so we can rearrange this, take 2a here and subject v squared. So you get u squared. V squared equals u squared plus 2as. And that is final equation. So everyone knows these equations, right? Like it's the basic stuff. But what everyone doesn't really tell you are the conditions under which you can really apply these equations, right? So there are a couple of limitations. Okay, so you need to make sure, and this is the first most important one, right? These equations when applying these equations, when using these equations, or wait, let me phrase it in a different way. During the time these equations are applied, acceleration has to be a constant, right? So you can't apply any of these equations for situations where acceleration is changing, right? So if it has to be a constant acceleration, right? Because why is that? If you looked at it, where we all started, we started with the definition of average acceleration, or we dealt with the situation of average velocity, right? So just taking the start and the end and dividing by 2 only works if there is a linear acceleration, right? For example, right, if we had a velocity that's changing like this, that means there is a constant acceleration. It's the same rate, same gradient, right? So if I wanted to find the average velocity here, I will just take 5, 0, and let's say this happened in 4 seconds. This is time and velocity, right? It will just be 5 plus 0 divided by 4, right? And that will give me the average velocity. But if my velocity was changing like this, right, that means the acceleration itself is changing, it's increasing, right? The gradient itself is increasing. So in that case, you can't neatly find the acceleration by just adding the high value and the low value and dividing by 2. That won't give you a nice average, right? So if you wanted to find the average there, you'll have to sorry, if you want to talk about acceleration, right, you will have to find the instantaneous acceleration at a given point, right? Or if this was a displacement time graph, for example, right, you will only can talk about uh, yeah, at a specific point rather than an average, right? So for this case, acceleration has to be constant. Second, and the most important thing you have to keep in mind, these equations have to be applied to a in a defined direction. Okay, so whenever you start a question, and you need to keep this in mind, write this in your own words if possible, right? Always draw a diagram and draw the direction that you consider as positive, right? Okay, so just draw a small arrow in the, so for example in this diagram, right? On the side, just for your own benefit, draw a small arrow and say this side is what I consider positive. Okay, so what that means is, again, direction is also relative. It depends on where you consider the positive is. Okay, so if you want to, in any question, you can pick any side as positive, right? But make sure you, even for the examiner to understand, make sure you draw it and say, okay, this side is positive. And make that a habit, because it will also avoid confusion for you when you're solving the questions. Okay, and since it has to be applied in a defined direction, make sure you what do you call it, use the components of the vectors in that direction. Right, so for example, if you consider this side as positive, and you had a vector pointing this way, you will have to kind of break it into those directions, right, that you consider as positive. Right, if it's a single linear motion like this, you'll have to break it in this direction. But obviously, if you're dealing with 2D space, you will have two directions to worry about. You'll have this side as positive and another side direction as positive. And then just you have to make sure you break all your vectors in those directions, because only then can you apply these equations. You can't apply them in a weird way, right? So the third thing you need to keep in mind is this is also a thing that a lot of people confuse. S, right, is the displacement that takes place in time t. So the paper really tries to mess you up with this. I know it sounds obvious, but they will give you questions where, for example, this thing is already starting at a given for example, let's say there is a ball or something like this, and it gets thrown or something like that, and it's already starting at 5 meters or something, right? And then when people apply their equations of motion, they will include that 5 and stuff. But the equations of motion only apply for the time period that you're considering. So if you're applying from t equals 0, okay, so depends on the, so if you are starting at t equals 0 here, what's the displacement it has taken? 0, right? And then let's say it comes and then falls here, then the displacement is -5 if you consider this as the plus direction. Okay, but that's for the whole period of time t, how much it has gone, right? So for a simple example, if the ball just goes up here and you want to find uh, let's say the height, the total height the ball goes up from the ground, right? You, let's say u equals, you use v, let's see, use the equation okay, so let's say you started with the initial velocity of 5 meters per second and you want to find the total height from this location to this location, and the time it took to go to the top is 2 seconds, right? So you use the equation s equals u plus v divided by 2 into t, right? So u is 5, v is 0 at the highest point, 2 multiplied by 2, and that will be 5. So you have s equals 5 meters. That 5 meters is this height from here to here. And then if you want to find the total height, you'd add this to that and say, okay, the total height h is 5 plus 5. Okay, so when you're applying the equations, the s is the displacement taken place in that time period t, nothing else. Okay, that's also where they kind of confuse you in MCQs. This is a simple example, but they might trick you into thinking, okay, it has already moved, and it confuses you. But you're always measuring from time t equals 0. What's happening, right? Okay. All good? Any how do you find these questions in general? Are they easy for you, or? Mm. Okay, cool. Yeah. I'll touch a bit on relative velocities and relative motion as well, if I have time today, but maybe not in too much detail. Okay. So the next heading we're going to talk about displacement time graphs. Again, like, these are very basic stuff, but the MCQs for these can be really confusing sometimes. They try to really mess you up with it. Okay, so what does the intercept of a displacement time graph tell you? So I'll just draw a displacement time graph here. Yeah, so basically the displacement, the existing displacement at time 0, right? It's displacement. Right. I think I used a bad example here. I think a more confusing example here would have been a situation where let's actually kind of talk about that a bit. Okay, so let's take that example again for a second. If I had something up here at 5 meters, and I tell you that this thing reaches a height of 8 meters. Okay, a maximum height of 8 meters, and it does this in a time period of 2 seconds. What is the initial velocity? Okay. First, what will you have to do? You'll have to define what is your positive direction, right? So I'm going to consider this as your positive direction. Always just mark that on your diagram. Next, you have to pick the right equation out of the 4 equations, right? Yes, right. So from the time of the motion to the top, it was 2 seconds. What is your initial velocity? So the reason why we have 4 equations is because you can see one variable is missing in each of these, right? So which equation should you pick first? Yeah, because we don't need acceleration to do that, right? So s equals u plus v divided by 2 into t. So what is the s here that you're going to put? I'm going to put 8. See, this is what I mean when it can get confusing, right? And this is what they do to mess you up in your MCQ, especially when you are in high pressure situations and you're trying to do it, right? So the displacement you should be putting is 3, right? Because the motion you're considering here at time t for the time period t equals 2 is the ball going from here to here, right? So v is going to be 0, right? We have 2 into 2, so u is going to be 3 meters per second. Yeah, so this I think is a better example to show how they can confuse you. Okay, so keep in mind these 3 rules. They are pretty simple rules, but these are the limitations of these equations. Okay, back to the displacement time graphs. Sorry, I took a small detour, but yeah. So that's about the intercept. Next, what do the coordinates tell you? Yeah, y coordinates give you displacement corresponding to time given in x coordinates. Okay. Can the x-axis be negative here? Can time go in the opposite direction? I just watched Christopher Nolan's Tenet yesterday, so everything goes back in reverse and shit. It was pretty trippy, but so unless we are living in Nolan's movie universe, time can't go backwards. So always remember your x-axis is 0. Right, you can't go this way, right? But your displacement can, right? So x cannot be negative, cause time can't be negative. Y can, right? Can be negative or positive. The pool this is called. Okay, so this, the third kind of thing we can analyze in a graph is the gradient. So we learned that the gradient is the slope, right? The slope tells you how y is changing with time. So if y is displacement and t is time, right? We're talking about how is displacement changing with time. So velocity, yeah. So the gradient at a given point will give you the instantaneous velocity, basically delta s over delta t, at that point, right? So by the way, that's why I kind of drew a curved kind of diagram, right? But again, in physics, you won't have to actually differentiate or calculate gradients like that. In most cases, it will be pretty easy to calculate the gradients, right? Okay, so what sort of information can you get, right? What information can we get from an ST graph? So displacement time graph. First is basically two bits of information, right? One will be how displacement is changing with time. Correct? What do we have to look at to get that, to get a feel for it? Again, the reason why we use graphs is because it's visual. Wrong. How displacement is changing with time. What do we need to look at it? The y values, right? Basically, the how y is what's a good word? Yeah, how y is changing essentially, or just you just look at the y coordinates, right? The y coordinates. Next is how velocity is changing with time. Here you'll have to look at the gradient. Okay, so simple example is we had something like this, like our first situation. What can you say here? You can say displacement is increasing, right? So how did you come to that conclusion? By looking at the y coordinates, right? The positive displacement is increasing. Yeah. So positive displacement is increasing. Velocity, again, it's a positive velocity. How are you saying it's a positive velocity? Because the gradient is positive, right? It's a gradient like this, right? If it's going this way, it will be a negative velocity. So first determination, it's a positive velocity, right? And you can see what is happening to the gradient. Imagine yourself walking along this slope. Yeah, the slope is getting higher and higher, so the velocity is increasing, right? If it was a situation like this, straight line, positive displacement is increasing, velocities, again, yes, imagine yourself walking on this, right? And you can see that the slope is the same, right? So the velocity is constant, right? So these are the two pieces of information you need to kind of feel when you look at a graph, right? So no math, nothing, but you can look at a graph and kind of get a idea of what is happening. And so this doesn't only apply for displacement time graphs. Later on in your life, when you have to deal with graphs, let's say you want to stay around in like engineering and maths and stuff, you'll have to deal a lot with graphs, right? And these graphs could be all sorts of stuff, right? Like we used the example of your cat last week, right? And feeding the cat and looking at its weight, right? So that could be two bits of information. Again, by looking at what is happening to your y values, you can interpret one piece of information, and then by looking at the gradient, you can interpret another piece of information, right? So those are the two biggest pieces of information you can get, right? So you can look at which side of the graph you're dealing with. That will tell you whether it's positive or negative. And then you can look at the actual y values, what's happening to them. You can see the displacement is increasing. And then you can look at the gradient and think about the slope, what's happening to the slope. So if the slope is getting steeper and steeper, that means the rate of change of that parameter is increasing. Okay, so try and kind of internalize that in your system, in your body, and that will be helpful. Okay, so that was displacement time graphs, and now we're going to talk about velocity time graphs. Okay, so your y-axis will be velocity. Again, time can't be negative, so this will be kind of cancelled out. So yeah, so that's all Einstein stuff. You don't have to worry about that. And no, you don't learn it in physics. With negative time. Sorry? Yeah, so interesting thing about gravity is it warps time. So for example, if you're in a higher gravitational field, time goes slower than in a, I know that's really screwed up to think about, but like for example, if you go, so gravity becomes weaker the further away you're from Earth, right? So imagine you climb up to Mount Everest, your clock, your watch will be ticking slightly faster than people who are at the bottom of in Colombo, pretty much, right? But it's really minuscule. But for example, if there's a really strong gravitational field, let's say you're close to a black hole or something, then it will really warp time, right? Just like again another Christopher Nolan movie, Interstellar. Did you watch Interstellar? Yeah, like how like they go near black hole and time gets screwed up. Yeah, but to really understand those effects and things, you need a bit more complex equations and stuff. Maybe they did it as an exercise in your school, but I don't think it will come in your exams. I'll have another look at the syllabus, but I doubt it. So have you started gravity as well? And isn't gravity after heat? You're doing heat now. I thought you said you're doing waves, optics. Both at the same time. Okay. Okay. Then I have a lot of catching up to do. Okay, cool. Okay, let's speed things up. So after October, I can actually spend a little bit more time because right now I'm also teaching at uni and I'm spending, yeah, yeah. So after October 31st, I will be able to maybe either have two classes or we can have more. I think it's better to have two sessions rather than one long 4-hour session for both of our sakes. Yeah. Okay, cool. Anyways, okay. So velocity time graphs. What does the intercept tell us? Initial. Yeah, initial velocity. Coordinates. Again, x gives us time. Y gives us velocity. Right. Gradient is how velocity is changing in time, gives us acceleration. So since in most questions acceleration is going to be a constant, most VT graphs we will be dealing with will be linear. Right? So the gradient will actually just be a straight line like this or something. Right? So area is also important in a velocity time graph. Yes. Right. So why does it give you displacement? Yes. Okay. So should give you displacement. So again, if you had a curvy kind of graph like this, you would have to do integration, right, to find the area under the graph. But since you will be dealing with linear graphs, yeah, you should do integration in maths. But since you're dealing with a straight line graph in physics, and your acceleration is constant, that will look something like this generally. So for example, so you're looking at point A and point B, and this is time t, this is time t plus delta t, and this will be u and v, maybe. I'll just call this t1 and t2. What will the area here be? It will just simply be this parallelogram, so it will be sorry, yeah, sorry, the trapezium. Your area will be u plus v, this plus this, into t2 minus t1. I'm just going to call that this, the time difference between these two, divided by 2. So what does this look like? Equation for displacement, u plus v into t. Yeah. So again, like by drawing the graphs, you can also derive those equations. They're all kind of interconnected. It's all part of the system. So what are the information from a VT graph? First bit of information is change in velocity with time. By looking at the y coordinates. The change in acceleration with time. Yep, change in displacement. So this kind of part you can visually kind of look at the graph and get out of it. So there's a set of really tricky questions that come. It's basically we have to convert displacement time graphs into velocity time graphs and vice versa. Right? And they can sometimes be slightly confusing when you're trying to do them. But these are the rules that you need to kind of remember. Converting ST graphs to VT graphs. Okay. The first thing you need to keep in mind is the change in the gradient of the ST graph has to be, right, the change has to match the change in the y coordinates of the VT graph. Yeah. So if I for example tell you convert this ST graph to a VT graph, right? The change of the gradient in this. So what's the change in the gradient in this? It's constant. There is no change, right? So that will mean the y coordinates of the y coordinates of the VT graph doesn't change. Yeah. So the gradient information in here has to be converted to the y coordinate values in here. Yeah. The change, right? Second thing, the change in y coordinates of the ST graph has to match the change in area of the BT graph. Right? Again, that makes sense, right? So remember last week we analyzed what happens to areas. We analyzed what happens to y values. Kind of go through those graphs again because this conversion can be a bit confusing sometimes, right? You need to look at whether the y coordinates are positive or negative, and then you have to look at whether the y coordinates are increasing or decreasing. If the y coordinates are positive and decreasing, how does that affect the velocity time graph's area? Right? You have to think in those terms. Okay, so go back to those examples that we discussed last week to understand what's happening with the y coordinates, the areas, and the gradients, and try to match them from them. I wish I had time to do questions with you because then we could have done a couple of examples. What you should do is you should start taking, if you can find a bunch of mechanics questions, past paper questions or something, start doing them, and maybe we can keep like half an hour to discuss difficult questions that you come across. Will you be able to find past papers like sectioned into the different units? Okay, actually doing genuinely the MCQs are harder than the big questions because the MCQ, sorry, yeah, because the MCQs really are tricky. They try to mess with you. So do the MCQs and then we'll try and if you come across problems like for example these conversions and things like that, we can discuss them. But can you actually do that like every day, like every week? Sorry, every week do a mechanics MCQ. Like give yourself 1 hour, time yourself. Okay, so another thing Samita used to do for us is, for example, if an MCQ paper is 1 hour, you have to finish it in 45 minutes. Right? it really trains you to think fast. Right? In the beginning, it's a training technique. Right? You limit the time, and you get used to doing questions in a short period of time, and after a period of like 2 to 3 months, you become like really good at that. So the thing is, it won't happen unless you do it yourself. So what he would do is he would give us these papers, we would take it home, and you have to be honest with yourself, time yourself, and try to finish the questions at a shorter time than you should, and then mark it yourself. Look at the answers, mark them, and then figure out where you went wrong, and then we can discuss them. Yep. So that will be my homework for you then. Just try and do a question set. So how does this book look like? In the sense, is it like, does it have papers? Yeah. Can we have a look? Okay. Okay, nice. How many years of past papers is that? Up to 2016. Okay, cool. So that's great. How many papers is that? Are there like separate papers, or is it like 1 hour separate papers? Or year by year? Yeah, my question is it like 40 question? Have they like bundled it into into 40 questions and 40 questions. Ah, okay, so they divided it in terms of units. Okay, so what you want to do then is, when you are sitting down and doing it, do it with that amount of time. So, so is it going in the same order that we're discussing now, like vectors and then equations of motion? Okay, cool. So can you then finish all the equations of motion stuff by next week? Yeah. Yeah. How many questions is that? Okay, your MCQ paper is 40, right? 50. And 50 MCQs, 1 hour. Okay, so yeah, so what you should do then is, how m- how many hours a week do you think you can allocate for this? 1 hour a week? Yeah. So if it's 1 hour a week and still you've only done this section, yeah. So till next week, can you do 25 MCQs from the linear equation section? And can you actually do those in 20 minutes? Yeah. So 25 questions in 20 minutes. The first 25 in the linear equation motion thing, right? Actually time yourself. Imagine you're in the exam. Put yourself under that pressure and do it in. Yeah. Okay. Okay. I give you. Yeah, that's kind of what you end up having to do, right? I mean, you have 50 questions, 60 minutes. That's yeah. So get used to doing it at like. Okay, just to start you off then. 25 questions, 25 minutes. Does that sound fair? Some of those will be quick, right? But that's the thing, like, might as well go through the pain now and get used to that, and then have to deal with the pressure of the exam. Yeah, think of it as training. Time yourself, block everything else out, and do it, and then take the rest of the few minutes to mark it yourself, and mark it honestly, right? Don't give yourself sympathy marks, right? And then what we'll do is we'll create a small Excel sheet, right? And we'll start like tracking your marks, and we'll see what sort of what you should be looking at when you're marking yourself is mark the questions that you found the most difficult, right? Because those are the areas that will keep bugging you, right? And the way to get better is to figure out what those areas are and get better at them, right? Because we don't realize time go by, and what happens is it's the same type of questions that keep screwing us over and over and over until the exam. So that's the advantage of doing practice questions. You kind of figure out what your weak areas are. So yeah, let's do that, and we'll spend like an additional half an hour every week, kind of like looking at your answers. Okay. Back to the lesson. So that will be your homework. Okay, so we're almost towards the end, right? Just a few more sections. So that's converting ST to VT graphs, and then obviously the other way around, converting VT graphs to ST graphs. Oh, by the way, before you do the paper, before you do the linear motion questions, go through this theory that we discussed again, right? That's another advantage. If you're doing it section by section, going through this is not going to take you that long, right? Don't try to memorize, just go through and try to understand and put it in your head before doing the questions. Okay, converting VT to ST graphs, right? The first thing is obviously the changes in y coordinates in VT graph have to match the changes in gradient of ST graph, right? And the changes in the area of the VT graph has to match the changes in what of the ST graph. Changes in the y coordinates of the ST graph. Yeah. Do you need to look at the gradient of the VT graph when you're doing this conversion? Can't hear you. Exactly, right? So don't waste your time, especially when you have less than 1 minute to do your MCQ, right? No point wasting time. Looking at the acceleration, looking at the gradient of the VT graph during this conversion. So those are the little things you need to kind of keep in mind when doing questions to save time. Okay, let's talk about a couple of examples under this section, right? And actually doing these examples will kind of help in your MCQs as well. So the first example we're going to talk about is vertical motion under gravity. So simple situation where we have some sort of object starting at point A, going to point B, and then coming back down, right? So we start with a velocity of u here at t equals 0. At the highest point, velocity is 0. Okay. Acceleration. Sorry. No, so if it's under gravity, you always have gravitational acceleration downwards. Yeah. So let's look at the motion from A to B. Right, from A to B will help you, and then we apply V equals u plus at in this direction. So let's follow the rules I mentioned. Let's consider this direction as positive, right? If we apply v equals u plus at for the motion from A to B, v is going to be equal to z, u is going to be u, a is going to be minus gt, right? I'm going to call this t1, right? Time from A to B, right? And t1, what direction? Whose direction? Yes, so no, I put the direction as negative for g. Okay, so you get to define which direction you consider positive. That's what I mentioned before, right? So I'm going to consider everything upwards as positive. That would make everything downwards as negative, right? So always start off in your diagram by marking which direction you consider positive, right? So now there's nothing stopping me by considering every direction downwards as positive also. If I do that, I'll still get the correct answers, right? But the thing is, if you're doing one, stick with it, right? So in the whole question, make sure you stick with one convention, right? So I'm going to stick with upwards as positive. So everything pointing downwards will be negative. So what is T1? T1 will be equal to U over G, right? So what is this? This is the time taken to reach max height. Okay. So the reason I'm kind of doing this couple of examples is this might be really helpful in your MCQs, right? For example, you might have MCQs where you need to figure out the time taken to reach the maximum height, right? In that case, you don't have to start off with v equals u plus at, substitute these and all that stuff. You can start off straight here. You know that the time to reach maximum height is just initial velocity divided by gravity, right? So that kind of tricks are the things you need to do to speed up your MCQs and quickly do things. I know it sounds scary, right? But honestly, you need to start getting used to doing mental math and doing things really fast like this, because you don't have time to do write everything nicely, especially in MCQs. And the only way you're going to gain that is by drilling question after question after question and then trying these out safely at home, right? Like you have no consequences at home when you sit down for 20 minutes and do a bunch of questions, right? No one is going to fail you. So try to use these like quick methods of doing things and get used to it, and then you will become like a physics genius pretty much, because everyone will be like, whoa, you finished the question so fast, and like you're using all these shortcuts and stuff, and like you'll get all these boys and stuff starting to like hit on you and I'm just kidding, that's not going to happen. That's never going to happen. You wish. Anyways, again, looking from A to B, if we apply v squared equals u squared plus 2x, right? Again, so I'm considering positive as up, right? So this becomes 0, this becomes squared, and then this becomes minus 2g s, and if I subject s, you get u squared divided by 2g. This is the equation for maximum height. Okay, so this is not physics, right? This part, I'm just teaching you how to maybe, possibly if you want to speed up your MCQ by also doing an example with everything that you learned today. And then if you're talking about the full motion, A to B to C, I'm going to apply S equals ut plus half at squared. So we are looking at the full motion, right? It's going up and coming down. What is the total displacement then? Yep. U is U. This time that I'm going to use here is T2, right? It's the whole time. And then G is going to be minus half G T squared. Okay. T2. I'm going to take T2 out, then I get U minus half G T2. What does this tell you if you try to solve this equation? At displacement 0, there are two answers for T2. Either T2 can be 0, that's correct, right, at the starting point, or T2 is basically this part is 0. Yeah, so it's 2U over G. Yeah. So this is the flight time, total flight time. And surprise, it's just twice T1. Yeah, that makes sense, right? So T1 is the time taken to reach the maximum height. Yeah, see, it's 2 into U divided by G, and T1 is U into U divided by G. Yeah, so that's example 1. Second example we'll be looking at is projectiles. Projectile motion under gravity. Okay, so imagine that an object and you throw it at an angle like this with a velocity v. Okay, angle theta. What's going to happen is it's going to go like this, but then gravity is going to keep pulling it down, and then it's going to eventually fall down. So remember I mentioned what's the first thing? You need to consider which direction is positive. So I'm going to consider this direction as positive and vertical direction, this direction as positive. Right? So you have two directions now that you have to worry about, horizontal and vertical. Okay. And what was one of the rules in the motion equations? You have to break everything to these two directions. Right? So I'm going to have the components of velocity like this. Right? So which direction is gravity acting? Downwards, right? So gravity will be downwards. So tell me, out of these two components of U, okay, I'll just call them Ux and Uy, just for, yes, so that's what I'm trying to get at, right? So what changes velocities? Acceleration, right? So what's the only acceleration here that you can see? Gravity. And gravity is always acting down. So out of Ux and Uy, who's going to get affected? Yeah. So Uy is going to get smaller and smaller, right? So Uy is going to look like this, going to look like this, going to look like this, and then going to be 0 at the highest point, right? While Ux is going to be the same size. Right? So if you really think about it, Uy is kind of acting pretty much like our previous example. Yeah, it's going to go up and going to fall down. If you don't consider the horizontal motion, it's behaving exactly as if vertical motion under gravity. Yeah. Okay, so what's going to happen next? If you think about vertical motion under gravity, it's going to go to 0 and then it's going to start accelerating downwards, right? So uy is now going to flip its direction, and here it was 0. It's going to start increasing again. While ux stays the same. Okay, so I've drawn the sizes of these arrows to kind of indicate it decreasing and increasing. Okay, so again we're going to look at 3 different locations. We're going to look at A over here, B over here, and C over here. And I'm going to consider this distance R. Okay. Let's first look at what happens from A to B. Right? Okay, so from A to B, first we're going to apply V equals U plus AT. So from A to B, V equals U plus AT, and I'm going to apply it to the vertical component. Okay, so drawing this arrow next to it also is an easy way of kind of telling you which side you're considering and which side is positive. Okay, so this is for the vertical component. What is going to be the final velocity of the vertical component from A to B? And then, yeah, what is uy in terms of theta? Yep, so you have u sine theta, and then minus g. I'm going to use t1 to consider the time to up to b. So t1 is going to be equal to u sine theta divided by g. Okay, so u sine theta is uy, right? Any sort of vertical velocity. So look at what the previous situation of vertical motion under gravity was, also u divided by g, right? So the initial vertical velocity divided by gravity will give you the time taken to reach the max, right? So time taken to reach max height. I'm not telling you to blindly study any of this. Obviously, you need to understand what's happening, but after you understand it, it might be helpful to kind of remember them, just to help you out with MCQs. But don't like study them in a dumb way without understanding how to derive them and stuff, because ultimately in the second part of the physics paper you will have to actually implement equations and stuff. Then we're going to do the same thing from A to B, just like we did in the vertical equations. We're going to apply v squared equals u squared plus 2as, 0 u squared sine squared theta minus 2gs, and then I get s equals u squared sine squared theta divided by 2g. What is this? This is the max height. Again, compare it with the previous equation, u squared over 2g. Yep. So the vertical motion is pretty much just motion under gravity. anyways, yeah, now let's look at the A to B to C motion, right? And again we consider this direction as positive, and then we're going to apply S equals ut plus half at squared. Total displacement is going to be equal to 0 again by the time it reaches C. U sine theta is going to be the vertical component, uy. So T2 is going to be the total time, and I'm going to get minus half g T2 square. And then again I can take T2 out like this, and then I get u sine theta minus half g T2. So I get two equations. One will be T2 equals 0, and the other is going to be T2 equals correct, twice the previous one. So this is total flight time. Okay, so we are also now going to look at A to B to C in the horizontal direction. So I'm going to consider this direction as positive, right? And I'm going to say S equals ut plus half at squared. Right, so from A to B to C, what is the total displacement that has taken place? R, right? R is going to be equal to u cos theta into t plus what's the acceleration? C. So R is going to be equal to u cos theta. By the way, this is T2. T2. So if you didn't know T2, you can actually get T2 from here, the previous thing, and substitute it here. Then you will get u cos theta, and you substitute it here, you get u sine theta over g, which will give you u squared sine theta cos theta over g. Okay. Because no one, in most questions, they won't tell you what the total flight time is, right? So there are a couple of interesting things. Yeah, so again, you know that from maths, you know that 2 sine theta cos theta is actually equal to yes, sine theta. So based on that, can you tell me what's the angle you should throw this to get the maximum range? So R is the range, right? Yes. Why is that? Okay, so look at this equation and tell me, right? For you to get R max given a certain velocity, what's the angle? Exactly, right? So to get R max, 2 theta will have to be 90 degrees for sine 2 theta to be equal to 1, which is the maximum sine can take. Therefore, theta equals 45 degrees for R max. Okay, so I'll wrap up with a small discussion about relative velocity. I'm not going to spend too much time, but just a simple um, sort of discussion about it. So, relative velocity of B relative to A means the velocity of B considering A is stationary. Okay, so that's kind of the definition of what it kind of means. I don't know why I put a 1 here. So relative velocity of B relative to A means that the velocity of B considering A is stationary, or in another way of looking at it is basically how A sees B move. Right? So imagine you're in position A and you're looking at something, right? So if you're looking at something, you consider yourself to be stationary. That's kind of the feeling that you have to get in your gut about it. Right. So terminology wise, for example, if I say SEA, this is I actually consider it the other way around usually. Yeah. So this would mean, actually I'll stick to the previous example. This is the displacement of B, sorry, this is what integration. So this is that's an S. Displacement of B relative to A, right? And this is the velocity of B relative to A, right? And this is the acceleration of B relative to A. Another important thing you need to know is this is equal to minus B relative to and also this is super important if you are considering the velocity of B relative to A and you had only the velocity of C relative to A, you can add the velocity of B relative to C and get this, right? So imagine you had the velocity of an object C relative to A and you had a velocity of B relative to C. You can get the velocity of B relative to A by just adding them up. You can kind of imagine as if this C gets cancelled off. Yeah, so all of this applies for displacement and acceleration as well. Okay. These two. Yeah, that's it for today. So we discussed everything to do with motion, basically. So there's an important term that you can use to describe what we discussed today, which is uh, kinematics. Let me see how it's, is it kinetics or kinematics? Kinematics. Yeah, so this is kinematics, right? Um, so everything we learned today is kinematics, right? So kinematics is basically the analysis of motion without forces, yeah. So everything that we um, describe today doesn't consider what's causing it, what's creating them to move, causing them to move, right? Everything we discussed today, if you knew the starting velocity, ending velocity, and the acceleration in between, or the time period between the starting velocity and ending velocity, we can describe the whole motion without even thinking about what's causing those motions to happen. Okay, so that's basically kinematics. That's just kind of like analyzing motion without thinking about the cause, what's creating it. From next week onwards, when you're talking about Newton's laws and stuff like that, we'll be talking about forces. So forces are what create this motion, and based on on that, we can kind of analyze what's happening to an object, analyze motion as well. So that's called kinetics, right? And that's what we'll be doing from next week onwards. Okay, cool. That's it for today, folks. I shall upload this video by tomorrow, maybe, in case you want to. The thing is, if you want to quickly go through any of this material, you can put it in like twice the speed on YouTube. Put it in twice the speed and just like listen to it. Very good. That saves. Once you get used to it, it becomes really useful. You can like quickly, like when you're traveling somewhere, going to school or something, just put it on twice the speed, and you can recap a whole section really fast. So hopefully, by the time you A levels get close, you'll have a bunch of videos that you can quickly kind of go through in case you need to understand. So, okay.